All right, students, let me try another video solution here. This one happens to be a capacitor, charging up a capacitor. And so if you kind of remember the discussion we had in lecture, it went something like this. I spent some time to do a discharging capacitor and said that we're out of time, but you get the same result as a charging capacitor. So if you take a power supply, a resistor, and a capacitor and make a single series circuit out of it, you'll get something to this effect. You could kind of plot the voltage on the capacitor as a function of time by realizing that this is, let's just say this is a 6-volt battery. Then what would happen is the voltage drop from our conservation of energy, our Kirchhoff's loop rule, is that we would lose voltage here and lose voltage here. And at first, there's no charges on here, so there would be no voltage, and so you would get a voltage that would be IR that at first would have to equal 6. And so you would say, well, I got 0 here on the capacitor, and then the voltage on the resistor must be 6. And then as current starts to flow, you'd begin to build up a little bit of charge on here. And so maybe the voltage on the capacitor comes up to 1 volt. Now remember, this total would have to always equal 6, so the voltage on the resistor would go down to 5. And they would follow kind of a path like this as the voltage keeps getting bigger and bigger on the capacitor, which makes more opposition, if you will, so the amount of current goes down, and so the rate of change changes. And so you're going to get something to this effect, where this could also be representative of the current. And so the current starts really high and decays away, and the charge starts at 0 and increases up. And so if we look at this charge on the capacitor, I'll say charge as a function of time, it equals something like this: 1 minus e to the minus TRC. Okay. And so let me read the problem here. It says a heart pacemaker fires 72 times per minute. Each time a 25 nanofarad capacitor is charged by a battery in series to, and then it says 0.632 of its full value. What is the value of the resistance? Okay, so I'll call this Q total, if you will, which again, the voltage would be then proportional to the amount of charge on it. So this equation is following this pattern here. And so what they're really saying here, if I grab my calculator, get it real close here, is they're saying, all right, it's going up, 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 and when it gets right here, which is 0.632 of its total value, that's enough to trigger the mechanism that sends the pulse to make the heart contract. So they're really saying this is 0.632 of the total. So we don't really know what the total actually is, and that's a good thing because they don't give us enough information to really decide that. We just have a percentage of what it gets to. All right. And so that way it cancels off, and we have this 0.632, and then 1 minus e to the minus TRC. Where if we then rearrange it, this becomes e to the minus TRC equals 1 minus 632. And that is the famous 37% or 36.8. I believe that'd be a 10, a 9, and a 9. Yeah, good. because this is one time constant. Here's what I mean by that. If I take a natural log now, well, let me do this side first. So I'll take the natural log of this side. So I get minus T over RC. And then this side becomes where's the natural log? Natural log of 0.368, and that should be the famous -1, one time constant. So -1. And so what they're really saying here, and you probably could have started this problem just right here, because that's kind of how they describe it in the reading, that it would take one time constant for it to build up to 63.2%. And so knowing that, you could start the problem and saying, all right, the time is one time constant. And I get the impression here that when they say the heart pacemaker fires 72 times per minute, each time a 25 nanofarad capacitor is charged and it's in series with the resistor, they're saying the time it takes to build this up is 60 seconds divided by 72. So that's the time to build up, and then it fires, and then it builds up and fires, and builds up and fires, and builds up and fires. And so that is a time of 60 divided by 72. And so about 83% of a second is the time required for it to build up. So in designing this pacemaker, the engineers need to say, okay, we need enough charge, so that decides how much capacitance to do, and it looks like they've decided that a 25 nanofarad capacitor would be enough. And so that dictates how much resistance needs to be put in series with the capacitor. So 0.833 divided by the 25 nano comes out to be 3.33 times 10 to the 1, 2, 3, 4, 5, 6, 7 ohms, which maybe I will write as 33 mega ohms. So pretty significant resistor. And I suppose I should also help you check the units here. Let's see. This side of the equation, I'll save a piece of paper and maybe do it right here, would be in seconds. And of course, we're trying to solve for resistance. And the other side is in farads. Now, remember, capacitance is charge per volt. So if I have units of seconds, and then I replace right here a farad with a coulomb per volt. And then I guess if I also remember that a volt here is an amp times an ohm. So got seconds over here. Then I guess I could do something such as this. I could bring the seconds over to here, leaving a 1 on the other side. And then I'd have coulombs per second, which is an amp, which cancels with that. And then bring the ohm back over. So in terms of units, not a surprise, it does work out to be ohms. So 33 mega ohms is roughly the answer. All right, hope that helped.